Suppose we have two lines, L, which is u plus lambda v, where lambda is a real number, and v is not the zero vector, and M, which is a plus mu b, where mu is a real number, and b is not the zero vector. We say that L and M are parallel if there exists a real number alpha such that v is alpha times b. In other words, to ensure that two lines are parallel, it is sufficient for the two direction vectors to be parallel. Let's look at a proposition. Suppose we have two lines L and M, where L is u plus lambda v, where lambda is a real number, and v is not the zero vector, and M is a plus mu b, where mu is a real number, and b is not a zero vector. We know that L and M are the same line. In other words, L equals M, if and only if the following two conditions hold. The first one is that v equals alpha times b for some real number alpha. In other words, the direction vectors of the two lines are parallel. The second condition is that L intersect M is non-empty. In other words, L and M have a common point. It is not hard to understand why these two conditions would guarantee that L and M are the same line, because the first condition implies that L and M are parallel, and the second condition guarantees that there is at least one point which is common in both L and M, which means that the two lines must coincide. Let's first prove the only if direction. Suppose L equals M. The second condition is trivial, because L equals M means that there are infinitely many points which are common in both L and M. Now let's prove the first condition. When lambda equals 0, we know that u is a point in L, which implies that u is a point in M, so u takes the form a plus mu1b, where mu1 is a real number. Also, when lambda equals 1, we know that u plus v is a point in L, so u plus v is a point in M, which implies that u plus v takes the form a plus mu2b for some real number mu2. Then, v equals a plus mu2b minus bracket a plus mu1b, which equals bracket mu2 minus mu1 times b. In other words, v is a scalar times b, so the first condition also holds. Conversely, we try to prove that L equals M by assuming that the two conditions L1 and L2 hold. By L1, we can write L equals u plus lambda alpha b, where lambda is a real number, by substituting v equals alpha b. By the condition L2, there exists a point C which is in the intersection of L and M. Now, C is in L implies that C equals u plus lambda naught alpha b for some lambda naught a real number, and C is in M implies that C equals a plus mu naught b for some real number mu naught. Equating the two expressions for C, we find that u plus lambda naught alpha b equals a plus mu naught b. In other words, u equals a plus bracket mu naught minus lambda naught alpha times b. Since we want to show that L equals M, and both of which are expressed as sets, we can use double inclusion to prove that they are equal. So first let's prove that L is a subset of M. So we take a general point in L which has the form u plus lambda alpha b. We can substitute the expression for u to get a plus bracket mu naught minus lambda naught alpha times b plus lambda alpha b. This equals a plus bracket mu naught minus lambda naught alpha plus lambda alpha times b. This is of the form a plus a scalar times b, which is in M. Hence, L is contained in M. For the other inclusion, we take a general point in M which has the form a plus mu b. Again, we can use the expression for u to write a as a subject to have u minus bracket mu naught minus lambda naught alpha times b plus mu b, which equals u plus bracket mu minus mu naught plus lambda naught alpha times b. To write this in the form of a point in L, we make sure that the second term is a scalar times alpha b. So we can multiply and divide the second term by alpha to get u plus mu minus mu naught plus lambda naught alpha over alpha times alpha b. Now this is an element of L, which implies that M is contained in L. So we have proved that L equals M. Let's look at the second proposition. Suppose we have 2 points x and y, which are distinct. Then there exists a unique line which contains both x and y. This is not hard to understand because x and y are 2 points on a real plane, so by joining these 2 points, we get a line which contains both points, and we cannot find another line which again contains both x and y, but is a different line. To prove this, let's first prove the existence of such a line containing both x and y. Note that y minus x is not the zero vector, because we have assumed that x is not equal to y. Now, let L be the line x plus lambda times y minus x, such that lambda is a real number. We have that x equals x plus 0 times y minus x, which is in L, and also y equals y plus 1 times y minus x, which is also in L. In other words, L is a line which contains both x and y. For uniqueness, suppose we have another line, M equals u plus lambda v, where lambda is a real number, that contains both x and y. We need to show that L equals M. By the previous proposition, it is sufficient to show that the conditions L1 and L2 hold. For the first condition, we know that x is an element of M implies that x equals u plus lambda 1v for some real number lambda 1. Also, y is an element of M implies that y equals u plus lambda 2v for some real number lambda 2. Hence, y minus x equals u plus lambda 2v minus bracket u plus lambda 1v, which equals bracket lambda 2 minus lambda 1 times v. In other words, we have written the direction vector of L, namely y minus x, as a scalar multiple of v, which is a direction vector of M. Hence, the condition L1 holds. For the second condition, since x and y both lie in L and M, x and y lies in L intersect M, so L intersect M is non-empty, which shows that the condition L2 holds. Let's look at one more proposition, which states that any 2 non-parallel lines meet at a unique point. To prove this, let L be the line u1, u2 plus lambda v1, v2, where lambda is a real number, and v1, v2 is not the zero vector, and M is a line a1, a2 plus mu b1, b2, where mu is a real number, and b1, b2 is not the zero vector. Suppose we have a point in the intersection of L and M, say C. It is sufficient for us to show a unique solution exists for such a C. Now, C is an element of L implies that C equals u1, u2 plus lambda times v1, v2 for some real number lambda. Also, C is an element of M implies that C equals a1, a2 plus mu times b1, b2 for some real number mu. Equating the two expressions for C and equating the components, we find that u1 plus lambda v1 equals a1 plus mu b1, and u2 plus lambda v2 equals a2 plus mu b2. Label these equations as 1 and 2. We try to solve for lambda and mu. Let's try to solve for mu first by eliminating lambda. So we take the first equation times v2 and subtract the second equation times v1. we get u1 v2 minus u2 v1 equals a1 v2 plus mu b1 v2 minus a2 v1 minus mu b2 v1. We collect the terms for mu and get bracket b2 v1 minus b1 v2 times mu equals a1 v2 minus a2 v1 minus u1 v2 plus u2 v1. We cannot divide the coefficient of u to the other side directly because there is a possibility that this coefficient is 0. However, we know that a unique solution exists for lambda and mu if this coefficient, namely b2 v1 minus b1 v2, is non-zero. So we assume for a contradiction that b2 v1 minus b1 v2 equals 0. Then we have b1 v2 equals b2 v1. Let's label this as star. If b1 is 0, then b2 is non-zero, otherwise b1, v2 is the zero vector. But also v1 is non-zero, because otherwise 0, v2 equals v2 over b2 times 0, b2, which implies that the two direction vectors for the two lines are parallel, which is a contradiction because we have assumed that the two lines are non-parallel. In this case, the equation star has the left-hand side equal to 0, but the right-hand side is non-zero, which is a contradiction. So we know that b1 is non-zero. Similarly, if we assume that b2 is 0, then b1 must be non-zero, and v2 is also non-zero, otherwise v1, 0 equals v1 over b1 times b1, 0, which again implies that the two lines are parallel. So from star again, we have that the left-hand side is non-zero, but the right-hand side is 0, which is a contradiction. So now we know that b1 is non-zero, and also b2 is non-zero. From star, we can divide both sides by b1 and b2 to get v2 over b2 equals v1 over b1. Let's call this alpha. So, v1, v2 equals alpha times b1, b2, which again implies that the two lines are parallel, again a contradiction. Since all cases lead to a contradiction, our initial assumption that b2 v1 minus b1 v2 equals 0 is false. In other words, b2 v1 minus b1 v2 is non-zero, which completes the proof. Let's end this video with an example. We want to find the point of intersection of two lines L and M, which are written as vector equations. To do so, we equate the two expressions for the two lines to get 0, 1 plus lambda 1, 1 equals 4, 0 plus mu times 2, 1. By equating the corresponding components, we get that lambda equals 4 plus 2 mu and 1 plus lambda equals mu. We can solve for lambda first by substituting the expression mu equals 1 plus lambda. We get lambda equals 4 plus 2 times bracket 1 plus lambda, which equals 6 plus 2 lambda, so lambda equals -6. We substitute the value of lambda into the expression for mu to get mu equals 1 plus -6, which equals -5. Once we have found the values of lambda and mu, we can substitute these values into the expression for L or M, so the required point of intersection equals 0, 1 minus 6 times 1, 1, which is the expression for L. This equals -6, -5.